This is section 13.3, vectors in the plane. Okay, so we are learning a new sort of number today. I use number loosely. So it's really a physical quantity or a way of defining something in the world. So when we measure things, we use numbers often. But just a number alone sometimes is not a good enough thing, is not enough to describe what's truly happening. So for example, a classic wonderful example to think about as we're learning what a vector is to think about the wind. So suppose you were flying a plane, or golfing, or kicking a football. In any of those situations, the wind really affects what you're doing. And there are two things about the wind that you need to know in order to hit your golf ball appropriately. One is the magnitude of the wind. Like, what is the actual wind speed? Is it really breezy? Is the wind blowing at 7 miles an hour, or is the wind blowing at 1 mile an hour? Is the wind blowing at 0.5 miles per hour? So one thing that matters is the actual magnitude of the wind. Okay, but just knowing that the wind is blowing at 5 miles per hour is not enough, because I also need to know, is this a headwind or is this a tailwind? Is this wind going to push my golf ball or my airplane further, or is it going to steer me off course? And so you also need to know the direction that the wind is blowing in. And this type of quantity is a vector. So when people say that the wind is blowing at 5 miles per hour out of the north, then it's actually blowing towards the south at 5 miles per hour, or you might think of that as 270 degrees. That's due south. Thinking about it this way: north, south, east, west. And when someone says something is happening, or if the wind is blowing 30 degrees north of east, then that would be this direction. Okay, so a vector is a physical quantity, something which requires both a number and a direction. Okay, so what is and we're going to talk about vectors in lots and lots and lots of different ways. There are lots of different ways to represent a vector, and we will talk about all of them today. And the first one is a geometric interpretation, and that is simply an arrow. There's an example of a vector. Okay, so with this vector, you have a few things to talk about. This is the initial point right here, the initial point, and down here is the terminal point. Most people don't use that language. They say head and tail. This is the tail, and this is the head. Okay, and we also say the magnitude of the vector. The magnitude is the length, and that's the number part of a vector. The length is the magnitude. Okay, so for example, in my 5 miles per hour, this vector would have a magnitude of 5. And then the direction the arrow is pointing in is the direction of the vector. Okay, so let's talk about vector equivalence. So, if the wind is blowing 5 miles per hour due south in Miami, and the wind is also blowing 5 miles per hour due south in Charleston, West Virginia, then that's the same wind. That's the same thing. The wind speed, the magnitude of the wind, and the direction of the wind are the same. And so the point of this is that a vector knows no location. So what we're going to do is we're going to plot these vectors on the xy axis, because we're in math and we love the xy axis. And so if I have a vector pointing directly northeast, so that's 45 degrees there, with a magnitude of 2, so the length of this vector is 2, and then I have another vector right here with magnitude 2, those are the same vector, aren't they? But they're just in different locations. So a vector is equivalent to another vector when it has the same magnitude and direction. The same magnitude, the same direction means the same vector. Okay, a zero vector has magnitude 0, and we write the zero vector as a 0 with an arrow on top. And so vectors do get names. Let's say that this is vector V right here, and this is vector W. And so sometimes we'll just put a letter next to it, but then when we're writing it out on our paper, we would write a W with an arrow over it, and then a V with an arrow over it. The book does this strange thing, and I've seen this in more than one spot, where they write like half of an arrow, and that's a vector. So that's what the book is doing. Okay, and now standard position. So standard position is when the tail of your vector is at the coordinate point 0, 0. That's when you have a vector in standard position. So over here, in this example right there, vector V is in standard position, but vector W is not, even though V and W are the same vector, they're just not in standard position. Okay, so this is just a little bit of an introduction to vectors. In college, you probably will see vectors, especially if you take a physics class. I mean, you'll see vectors the entire time. Vectors are huge. Vectors are used in a lot of different applications because a lot of times a number doesn't suffice. You need a direction as well. Okay, so when in college, my point of that was, when you are in college and someone says, what is a vector? The standard correct answer is something that has both magnitude and direction. That is what a vector is. Something that has both magnitude and direction. Okay, so what we've done with this introduction is I've just given you the idea of what a vector is. It has magnitude and direction, and we've drawn a couple of arrows, and we've talked about some terminology. So the most useful way of using vectors quantitatively is to write the vector in what is called a component form. So yes, every vector has magnitude and direction, but let's talk about the component form of that. So for example, let's go ahead and use my 5 mile per hour wind, and let's say that that's pointing in a direction of 53 degrees north of east. So I have 50 miles per hour wind at 53 degrees north of east, or just at 53 degrees whenever you're a vector in standard position from trig. Okay, so what that means is I'm going to stick this on the XY axis, and I'm going to put this in standard form. So 5 miles per hour wind, 53 degrees, and I'm going to draw this vector in standard position. So I'm going to put the tail at 0, 0, and 53 degrees is not out of nowhere. That's your 3, 4, 5 right triangle, where 4 is the X, I think. Let's see. Nope, it's the Y. Okay, so I'm going to go to the right 3, and then I'm going to go up 4, and this ends up being 53 degrees right here. Okay, so that's your vector. This is it. It has length 5, and another reason why I know it has length 5 is I've designed this vector to be the hypotenuse of a 3, 4, 5 right triangle. And so thinking about a vector as the hypotenuse of a right triangle is how we put the vector into component form. The x and y components of the vector are simply the 2 legs of the right triangle. So this 5 miles per hour at 53 degrees is the same as going 3 miles, as a wind that blows you 3 miles per hour east and 4 miles per hour north. And so if you are traveling due north, you will end up drifting to the east. But whatever your plane speed normally is, you're going to gain 4 miles per hour in your northerly direction. So the component form of this wind, or the way we talk about this vector, is we would say that it is 3 in the x, positive 3 in the x, because I happened to move towards the east, and 4 in the north. And so that's like x and y, but I don't want to use parentheses here because that's the coordinate point 3, 4, which incidentally is the terminal point, or the point of the head of the vector. But instead, when we're writing a vector in which you need direction, it means start at 0, 0, go to 3, 4, go 3 to the east, 4 to the north, or positive 3 in the x, positive 4 in the y. Okay, so this is the component form. The component form has an x component and a y component. Looks just like a coordinate point, except we use pointy brackets. That is actually what we call them, pointy brackets. And so here I have an example. We have a vector, and the initial point is at 2, negative 3. And the terminal point is at 4, 2. And so that means I point like this. And now the task is to put this in component form. So you need to determine what is the change in x. Well, for the change in x, I happen to go right again. I keep having to go right and north. But you don't always have to go right and north. You could have gone south or west, and in which case you would use negative numbers for the components. We will get to some of those. All right, so I started at 2, negative 3, and I went to 4, 2. So in the x direction, my component changed from 2 to 4, which means I went right 2. And then in the y direction, my initial point went from negative 3 to 2. Negative 3 to 2, so that was up 5. And so that is the vector in component forms, 2, 5. Okay. So now that we have vectors and we know about how to write them in component forms, we really want to do some math. So we're going to add vectors together and we're going to multiply them by a scalar. So geometrically, when you add two vectors together, this is just like a treasure map directions. So I'll give you one vector in which I'll say 4 paces due south, 3 paces due east, then now go 5 paces north and 6 paces west. So you just do one and then the other. So you would go one vector and then the other vector. I forget what my two vectors were. But at the end of the first vector, so it's like you're walking. You start at the initial point, you go the direction of the vector, the amount the vector tells you to go, you stop, and then you go in the next vector. And so then the result is, well, I started here and I ended there, so that's my result. It's called a resultant vector. It's the result of adding two vectors. So if I took vector A and vector B, and I added them together, it's the same as just going vector R. In component form, this is simply just adding the components together. Because if I have you go right 3 paces and then left 2 paces, that would be 3 and negative 2. That would overall be right 1 pace. And that just works out from adding. Scalar multiplication is when you take a vector and you increase the magnitude only. You're not changing the direction, you're just increasing the magnitude. So when you have a vector b, like that is this amount in this direction, 2b is the same vector, however, just one added to the other, or you could think about it as just having twice the magnitude. So there's 2b. Okay, so here I have an example, and there are a lot of different tasks. So here we have vector u and vector v. Vector u is 3 right, 4 north, and v is 2 left, 2 north. So the first thing we're going to do is what is vector u plus v? By the way, notice that these down here are just bolded. Sometimes in type, for a vector, you only bold the letter. Sometimes you bold it and you put the arrow above, like I did in these ones. Okay, so for vector u plus v, but when you're writing with your pencil, you can't bold, so you put an arrow on top for sure. For vector u plus v, I'm going to take the components of u and add them to the components of v. So that means I'm going to take 3 plus negative 2, and that is 1. Then for the y component, I'm going to take 4 plus 2, and that is 6. And so the vector u plus v is simply 1 to the right, 6 to the north. Okay, 3v means I'm going to take my v vector, and I'm going to just multiply it by 3. So that's 3 times negative 2, 2, or negative 6, 6. Okay, negative u is just opposite u, and in that you just negate your component. So negative 3, negative 4. And now v minus u is just v plus negative u. So I can take negative 2 and negative 3 and get negative 5. Or you could think about it as -2 minus 3. And then for the y component, I'll have 2 and -4. So it's -2. And then why don't you go ahead and do 2v minus 3u for your homework. So go ahead and pause this, double the components in u, triple the components in v, and then subtract, and you will get one vector. Okay, so once you're done doing that, unpause, and there are 9 properties of vector addition and scalar multiplication. These properties are on page 827 in your book. Page 827. And they're telling you that addition is commutative. So u plus v is v plus u. They're saying in the 0 vector, you add that to anybody and you get itself. A lot of properties of vectors are very nice, just like the numbers. And so we're not going to take the time to write them down. 0 times any vector is 0. 1 times any vector is itself. And so we don't need to write those down. Okay, before we continue on, I think I forgot to find the magnitude of the vector that we did in this example. And I want to make sure we know how to find the magnitude of the vector. Back to this example where we took an initial point and a terminal point and determined the vector and made the magnitude of the vector is the length of the vector. And so you're just finding the hypotenuse of this right triangle. So here, this length is your magnitude. So how do you find the length of the hypotenuse of this right triangle? You use the Pythagorean theorem. We just take it away from it. 2 squared plus 5 squared equals, so if I call this vector b, equals the magnitude of vector b. And so magnitude it's like an absolute value bar, or an absolute value sign. And so when written around a vector, it's telling you how big the vector is. Just like absolute value of -7 tells you the magnitude of that number away from 0, 7 away. Okay, so what's the magnitude of b squared? Because it's the Pythagorean theorem. So we want to do the square root of 4 plus 25, and that's the magnitude of b. So it's the square root of 29. And in general, the magnitude of vector is the square root of the x component squared plus the y component squared. So this means the x component and the y component. Because it's just the Pythagorean theorem. All right, moving on. With that in mind, we're going to talk about what a unit vector is. Unit vectors are really helpful because the magnitude doesn't get in the way of the direction. So it pretty much just tells you the direction of the vector, and we always just make the magnitude equal to 1. That's why it's called a unit vector, because the magnitude is 1. And it's just when we only want to know the direction. Okay. It's because, and that happens when we want to go in the right direction, but we have a specific magnitude we'd like to use. So we would like to have a vector that just describes direction, and then I can multiply it by the magnitude I'd like to have. And that's actually how we get the magnitude of a vector, or the unit vector for a vector anyway. So let's say I have a vector b, okay, and I need to make it into a unit vector. So to make it into a unit vector, you simply use the vector it is itself and divide by how long it is. Because when you do that, you scale back the vector by its length. You scale the vector back by its length, and so now it's only magnitude 1. All right, let's talk about that with specifically this example. The vector in question is -3, -7. So if I put this in standard position, and I just plot the point -3, -7, okay, then that would be the head of my vector. And so we're talking about this vector right here, b. It has sides of magnitude 3 and 7, but it goes left 3, down 7. So obviously the length of b is not 1, okay? How long is b? Well, we just did that. We're going to take the x component and square it, and the y component and square it, and you get the square root of 9 plus 49, which is 58. So this vector is the square root of 58 units long. That's between 7 and 8. Between 7 and 8 units long. I want it to just have length 1. So in order to do that, I take this v, and instead of multiplying it by, because if I took this vector v and I multiplied it by 2, then I would add it to itself, right? This is 2v. This red vector, its magnitude, is double the original magnitude of v. So it's 2v. And so I've made it twice as long as it was. I don't want to go that direction. I actually want to scale it back so it points in the same direction, but its length is only 1 unit long. So if it is something like 7 units long, and I want it to be 1 unit long, then I take these components and I divide them each by 7. And that will scale each of those x and y components back enough so that the magnitude is only 1. Okay, but it wasn't 7, the square root of 58. So I'm going to take 1 over the square root of 58, and I'm going to multiply it to -3, -7. And this is the unit vector. Kind of ran out of room. So the unit vector is -3 over square root of 58, -7 over square root of 58. And we will not rationalize that denominator. That would be ridiculous. So that is our unit vector. Okay, we have 2 special unit vectors, super special unit vectors. So special they get their own name, like pi does, and Euler's number. They get their own name. These are the I, J, and there's actually a third one called the K vector. These are the unit vectors that work in the 3 dimensions we understand as space. So the I vector is 1, 0. That is this vector that points in the positive x direction. And the J vector is the one that points in the positive y direction. I wrote them with arrows over top. I doubt I will ever write them this way again. I tend to give them hats instead of arrows. And that hat means it's a unit vector. It means it has length 1. So that's I hat and J hat. So instead of dotting them, I put a little hat on top. Okay, and so one reason why these unit vectors are so special is because every vector can be written in terms of them. So let's go back to that vector v, who was -3, -7. In standard position, remember he pointed left 3, down 7. And so from tail to head, or initial point to terminal point, this was v. Remember, we found the unit vector by scaling it back. But if you think about how vectors add geometrically, if I were to just go 3 left, and then after that go 7 down, well, I would have a resultant vector of the vector v, -3, -7. And so what we're saying is, well, v is the same as -3 left, right? Isn't this the vector that does nothing in the y and just goes 3 in the left? Followed by, or plus, the vector 0, -7, that which does nothing in the x, but just goes down 7 in the y. Okay, and this is kind of just semantics. And then you can factor out these numbers. And then you see these I and j vectors. So vector v is -3i plus -7j. And so this is called unit vector notation for vectors. Oh, wait. And standard unit vector notation. The wording is maybe different. But so vector v. Okay, now we have 3 representations. 3 representations for this vector. The very first one was this, vector v. He happens to go 3 to the left and 7 down, but that's the vector v. It's just the picture that is v, who has magnitude and direction. Or we learned you can write that in component form, which component form is the best form. It's the way you do the math on the vectors. And this is very similar, exactly the same as unit vector notation. -3 in the x plus -7 in the j. That plus a negative, you don't have to write that. You can just write it like this. It's the same difference. But I and j are vectors. They're very specific unit vectors. Okay. Now we're going to do something important. We're going to learn about another way of writing vectors. And actually, we've already discussed it. Remember that the definition of a vector is a quantity that has both and, okay, and I want you to fill this in. You really need to remember that. It's actually just right here. Okay, so our -3, -7 was components. I'm going to go and I'm going to write some letters here. So let's call it vector B, and I'm going to give it x component, y component. And the other way of talking about a vector was just by saying, hey, 5 miles per hour due south, because that has magnitude and direction. That is a vector. And so now I want to talk about there are specific formulas to get back and forth between. So let's say I'm going to just draw a vector in standard position, and I'll go ahead and make him have positive x and positive y, but it won't matter. Okay, so the magnitude of vector B, we already talked about that. That's the square root of x squared plus y squared. And, or you would say that the magnitude of vector B squared is x squared plus y squared. Also, if you look at this angle theta right there, when a vector's in standard position, then theta is the angle that the vector makes. Then the tangent of theta is the y component divided by the x component. Also, if you were to do the sine of theta, that would equal y divided by the magnitude of the vector. And then I multiply both sides by the magnitude there. And then if I were to do the magnitude of the vector times the cosine of the angle of x, that is the x component of the vector. And so you are going to be converting back and forth between components and magnitude and direction, and it is exactly like polar form, rectangular form. Exactly the same formulas. Where this magnitude of v, that we call r. It's the radius from the origin, right? Same thing. R sine theta is y. R cosine theta is x. R squared is x squared plus y squared. So those are the exact same thing. Yay! Okay, so let's do some examples here. I know I'm taking a long time. All right, so what are the magnitude and direction? Well, the magnitude of A, this is just the Pythagorean theorem, square root of 3 squared plus -3 squared, square root 9 plus 9, so that's the square root of 18, or 3 radical 2. So my magnitude is 3 radical 2, and my direction, well, the tangent of theta is y over x, -3 over 3, or -1. So theta has a reference angle of pi-4, and I need to figure out the correct quadrant. So where does this vector point? Well, it goes right 3, down 3. So that is certainly the fourth quadrant where the angle is 7 points. Okay, now you do B. Thanks for homework. And now we're going to go backwards. So now we're going to do 2 more. So now let's go the other way. Here I have magnitude 7 at 142 degrees. So that means where's 142? He is like here somewhere. And the length of this is 7. So what are the x and y components? So in order to do that, I actually do need to figure out this reference angle. The reference angle would be 180 minus 42, 38 degrees. And so my x component is just going to be 7 times the cosine of 38. Or actually, you can go ahead and put in 142. There's no need to do the reference angle. Previous cosine functions will give you a negative. And then y is equal to 7 times the sine of 142. And so my vector A, written in component form, is negative, ends up being negative 5.8, yeah, negative 5.52, and this is 4.31. And notice it does match up. We know that matches up to something pointing towards the second quadrant. And so we just write this as negative 5.52, comma, 4.31. All right, so you do B, vector B, magnitude 2, the direction angle is 300 degrees. Good news, 300 degrees, you can do that without a calculator. Okay. And, oh, that's it. All right. We'll see you tomorrow.